So the other common mechanism of nucleophilic substitution reactions is unimolecular nucleophilic substitution, or SN1 reaction. In such reaction, reaction rate depends only on the concentration of the substrate. So in general terms, reaction of alkyl halide, for example with water, gives alcohol and molecule of hydrohalic acid, hydrogen halide, as a byproduct. Rate depends on rate constant and concentration of substrate, alkyl halide. You see, it doesn't depend on concentration of the nucleophile. Here is an actual example. A reaction of tertiary butyl bromide, or 2-methyl-2-bromopropane, with water gives tertiary butanol and hydrogen bromide. Reaction rate depends on the rate constant and concentration of tertiary butyl bromide. You see, it does not depend on concentration of nucleophile, water. Again, you need to know this equation, but there will be no calculations. Some of the features of an SN1 reaction are that it is unimolecular, it proceeds with racemization, and rate decreases with decrease in the degree of substitution at the reactive center. Unimolecular, you have just seen that. That's rate expression. Proceeds with racemization, so that's obviously very different compared to inversion of configuration. So stereochemical outcome is different. Very different from SN2 reaction. So obviously very easy to distinguish one mechanism from the other. And here you can see experimental data that alkyl halide, alkyl bromide with water at 50 degrees reacts in SN1 reaction to give corresponding alcohol. And so if this R is methyl group, actually reaction does not proceed through SN1 mechanism at all. Rate is very slow, and it's 1.05 relative rate due to SN2 reaction. Primary also in general are considered not to react under these conditions, SN1 conditions, but rate would be 1. Then we set that as 1, and then expressed relative to primary. Secondary reacts at a rate of 11.6, so approximately 12 times faster. So secondary substrates can react under SN1 conditions. And tertiary react very fast, 1.2 million. So tertiary really fast. So that's the order of reactivity. Tertiary very fast, secondary much slower. Primary and methyl don't undergo SN1 reactions. And so you can already see some regularity here that in case of SN2 reactions, we have the opposite order. So primary and methyl underwent SN2 reactions, while tertiary did not. So as you can see, it's only secondary substrates that can undergo both SN1 and SN2 reactions. For the rest, it's either SN1 or SN2, and that's always first thing that what you look for. What is the nature of the substrate? Is it methyl, primary, secondary, or tertiary? When we consider the reaction mechanism, it consists of two steps. First step is the rate determining step, and it's formation of carbocation. Of course, rate determining step is the slow step. It involves breaking of carbon leaving group bond, in this case carbon-bromine bond, to give the intermediate carbocation. That's why it's slow. It involves only bond breaking. Second step is fast step. It involves only bond formation, where nucleophile donates free electron pair to form a bond. That's so-called product determining step. And this is the end of the reaction mechanism after second step, formation of oxonium ion. But since this oxonium ion is not stable, it loses proton, and so there is additional acid-base step, proton loss, to give the final product, in this case alcohol. But first two steps are substitution, SN1 substitution. Third step is simply acid-base reaction to remove the proton from the product. And now, from knowing the mechanism, you can guess why reaction proceeds with racemization. Because if you start with chiral starting material, like R2-bromobutane, first slow step involves loss of bromine to give intermediate carbocation. Carbocation is planar. It's sp2 hybridized and trigonal planar with angles of 120. Now, this carbocation basically has no memory. Same carbocation is obtained from R2-bromobutane or S2-bromobutane, because once bromine is gone, we end up with same planar carbocation. And now nucleophile, in this case water, can approach this carbocation from the top or the bottom with equal probability. Of course, free electron pair is donated into this empty orbital. So approach is from the top or the bottom with equal probability. And so 50% of the water molecules will approach from the bottom to give S2-butanol and 50% from the top to give R2-butanol. I think that would be, actually, let's see. No, I made a mistake. 50% would, yeah, this S would be from the bottom approach. Not if that's what I have. My memory is a bit going. Bottom approach, you can make models and convince yourself of that. Bottom approach gives S in this case, and approach from the top gives R. But either way, bottom and top are 50-50, so we get racemic mixture. And here is the same equation shown with Fischer projection factors. Now, frequently in these reactions, sometimes depending on reaction conditions like concentration and temperature, we get incomplete racemization, and we get more of one enantiomer than the other because of the complexation of the solvent and so on. Don't worry about that. If you get 60-40, 55-45, that's still racemization, and it's still SN1 mechanism. Because if it's SN2, we will get 100%. R2-bromobutane would give S2-butanol 100%. There will be no partial racemization. Now, for cyclic systems, you don't need to know that, but in cyclic systems, when reaction proceeds through SN1 reaction mechanism, then we always get one enantiomer predominantly, or one stereoisomer predominantly. That's because approach from two sides to the intermediate carbocation is not equally easy. It's not the same. Two pathways are not the same. So one is favored over the other, but that's only in cyclic systems. We still get a mixture of the two, but in this case, one stereoisomer clearly predominates. You don't need to worry about that. This is a little bit more advanced stuff, so you will not be tested on that. So this top part of page 302, reaction in cyclic systems, you don't need to. If you know that, that's good, particularly if you're interested in that. If you go on to study more organic chemistry, you will be covering things like this, but you don't need to worry about this. This is an example of reaction that is stereoselective, but not stereospecific. Because typically SN1 reactions are not stereoselective, and of course, if they're not stereoselective, they're not stereospecific either. But this is an exception. In ring systems, they're stereoselective, but not stereospecific. Of course, SN2 reactions are both stereoselective and stereospecific. And so now we should look at factors that affect the rate of SN1 reactions. And those are degree of substitution, nature of the leaving group, nature of the nucleophile and the solvent, and rearrangements. That's a very important factor last time. So degree of substitution, that reflects degree of stability of carbocations. So tertiary react readily at high rate, very fast rate, then secondary, primary don't undergo SN1 reactions. That's because primary carbocations are unstable. Tertiary carbocations are very stable, and so they readily undergo reactions. Okay, now, when it comes to nature of the leaving group, a leaving group would easily leave to give corresponding carbocation. So good leaving group will react at high rate, while poor leaving group at low rate. But basically, effect is the same as SN2 reactions, which means that alkyl iodides react at the fastest rate, alkyl chlorides at the slowest, alkyl fluorides are unreactive. In case of SN1 reactions, usually nucleophile is the solvent, and reaction is solvolysis. If solvent is water, then we will call it hydrolysis. If it's alcohol, alcoholysis. And typically solvent is, or nucleophile is a weak nucleophile in SN1 reactions. You will see when we compare SN1 and SN2 reactions, typically weak nucleophile favors SN1 reaction. And then very important, rearrangements. If you learned rearrangements from chapter 9, then this is trivial extension. If you didn't, then that's a little bit of a problem. So since carbocations are reaction intermediates, then whenever secondary carbocation forms, it will rearrange into more stable tertiary carbocation. Primary carbocations usually don't form because they're not reasonable reaction intermediates. They're not stable enough. So primary substrates will react through SN2 reaction mechanism, and so no carbocations as reaction intermediates. But secondary and tertiary compounds will react through SN1 reaction mechanism. Tertiary carbocation is already stable, so no rearrangements. But secondary carbocations could rearrange into more stable tertiary carbocation. So whenever you have secondary carbocation, check what is next to it. Because if shift of a proton, or actually hydride anion, H minus, shift of hydride anion, or methyl group or small alkyl group can result in formation of tertiary carbocation, then rearrangement will occur. And so reaction that gives rearranged products. So rearrangement occurs to give rearranged products. Rearrangement means carbon skeleton is rearranged. So note that here we are starting with 2-bromo-3-methyl-butane, and we end up with 2-methyl-2-butanol as reaction product. So you see methyl was next to leaving group. Now methyl was on the same carbon as the hydroxyl group. Don't worry about primary substrates and possibility of rearrangement. That's here given only as curiosity. I definitely would not test you on this and would not expect you to know this exception. Because primary substrates, you should assume that primary substrates don't react by SN1 mechanism. There are exceptions, but at this level, we don't expect you to know these exceptions. Sometimes when I have more time and I may cover this course at a bit higher level, and that's certainly not the case over the summer when we have 6 weeks, then I may go a little bit over it. But now, don't worry about that. And that's also part why you need to attend these lectures, because I tell you what you don't need to know for the exam, because otherwise then you would be, if you're not attending lectures, then you really need to cover everything. And we have 6 weeks course, and you may not have as much time to cover that very well if you're focusing on things that you don't need. Previous rearrangements involved hydride shift. Alkyl shifts are also common. So again, secondary carbocation. In this case, there are no neighboring hydrogens that can shift, but alkyl group can shift, and then shift of alkyl group gives tertiary carbocation, and then reaction with a nucleophile followed by loss of proton gives the final product. Alkyl shift is called Wagner-Merwine rearrangement. You need to be familiar with that name, because sometimes exams such as MCAT will ask you what is the result of Wagner-Merwine rearrangements of the following carbocation. And that simply means rearrangements of carbocation, alkyl group shift. But if you don't know what it means, you may think it's something fancy and not be able to answer that question. And MCAT is very big on that, on asking those names. Do you know those names? Do you remember those names? For the name reactions and name processes like Wagner-Merwine rearrangement. That's because medical school is like that. You need to know all the names for various diseases and disorders and so on. And so they want to see, can you remember them and can you relate them to a particular phenomenon? Do you know what they mean? So you need to know what Wagner-Merwine rearrangement is. It's simply alkyl group shift, cationic, typical ordinary cationic rearrangement. So that's all you need to know about SN1 reactions. I'm going to stop recording here